So I'd like to visit the concept of an empirical and molecular formula paired with an example that can help us understand what the relationship between an empirical and molecular formula is and what they actually mean. So the empirical formula, well, let's first start with the formulas that we're used to. We're usually used to looking at molecular formulas. In other words, if I had C as carbon and I had, let's say, 6 of them, and I had hydrogen as well, and I had, let's say, 12, then this is something that we're used to seeing. Well, you can conceptualize this to say that you have 6 carbon atoms and 12 hydrogen atoms, but and so this would be deemed as the molecular formula, right? Because it is a molecule, and it is a formula telling you how many carbon and hydrogen you need to form this molecule. But the empirical formula, and this is where you kind of enter new domain, the empirical formula is actually it is actually a reduced version of the ratio of atoms of the molecular formula. So what I mean by this is if you were to sort of compare, just sort of look at the ratio of atoms in this particular molecule, you could say that for every 6 carbon atoms, right, you have 12 hydrogen atoms. And you would need this to sustain this particular molecule. But you'd recognize that the ratio, it can be expressed as a fraction, right? You could say that this is 6 over 12, or you could say that this is 12 over 6. So long as your carbon and hydrogen, or really the other way around in that case, so long as you're expressing hydrogen and carbon sort of in the same, with their accurate atoms, this stands. But what I'd like to sort of bring up here is that you can actually divide both sides of the ratio, this side and this side, by any number. And the ratio as a value proportionately would remain the same. And that's simply because, if you're working with a fraction, I express this ratio as a fraction. If you essentially multiply or even divide both numbers by the same quantity, the denominator and the numerator by the same quantity, you are going to be left with an equivalent proportion, an equivalent fraction. And so if I were to divide both sides by, let's say, 6 in this case, I would have 1, and I have 12 over 6, which would just give me 2. I'd have 1:2. So in other words, I could just express this ratio as being 1 carbon atom and, let's say, 2 hydrogen atoms. And that's what you would call the empirical formula. So really, this relationship here is saying that it's essentially saying that you have your molecular formula, which is what we have here, and the reduced version of the ratio of atoms would be your empirical formula. And you know that it's your empirical formula because you cannot reduce the ratio of atoms any further. So, and another thing that you want to essentially be able to connect here is that the empirical formula, it's a reduced form. The molecular formula is it's not a reduced form. It's an unsimplified form of their ratios. But one connection here is that the molecular formula will always be a multiple of the empirical formula. In other words, if you were to look at the molecular formula here and compare it to the empirical formula and really just look at the ratio of atoms, you could evidently see that the molecular formula is 6 times the empirical formula. And so, because if you were to multiply this by 6, right, if you were to have 6 times the empirical formula, you would essentially have 6 carbon and 12 hydrogen, right? You would essentially multiply the subscript here by the number outside, and you would get back the molecular formula. So the molecular formula is a multiple of the empirical formula. And another thing that I want to sort of add here, just sort of piggybacking off that fact, is that if you had the molar mass of this particular molecule, and you had the molar mass of this particular molecule, then the mass would reflect this, the mass would reflect the fact that the molecular formula is 6 times the empirical formula. And so if you had your empirical formula mass as being 108 grams per mole, then given that the molecular formula is 6 times the empirical formula, your molecular formula will be 108, but multiplied by 6. It's 6 times 108 grams per mole, 6 times the empirical formula. So this relationship between atoms is also consistent between the masses. And that makes sense because, of course, atoms themselves have mass. And so if you have 6 carbon and 12 hydrogen, and each atom would essentially consume mass, and that mass reflected with the empirical mass would be 6 times the mass of the empirical. So that's just a note there when working with empirical and molecular formulas, a very important note that helps us understand the relationship. And so if we can sort of apply that concept to this question here, it asks us a compound contains 52% or 52.14% carbon, 13.13% hydrogen, and 34.73% oxygen by mass. And that by mass part is so important because it's telling you that, of the entire compound, how much does each of these elements consume of that entire compound in terms of mass? So like, let's say in terms of grams. So that is important to recognize that it's by mass, but the empirical formula would concern itself with atoms. The empirical formula does not concern itself with a ratio of mass. The empirical formula, or even the molecular formula, concerns itself with a ratio of atoms. So if you were to think that, let me go ahead and take the percentage in each of these cases, make a ratio, and then sort of reduce that ratio, you would get a ratio of mass. You would not get a ratio of atoms. So that is sort of the key differentiation here, and why we can't actually do that ratio in terms of mass. We want to find another way. So now that I'm on the topic of the other way, one thing to sort of remember here is that there is a very simple brute force way of doing this. And I'll actually go ahead and sort of show you the brute force method, but then I'll tell you why the brute force method works. So the method, and this is sort of the method that you would sort of, there are sort of 3 methods in this case. So there are 2 methods, and then I'm going to sort of explain why each of those methods actually work. So the first method is and this is of course solving A in this case, finding the empirical formula. The first method in this case would be to essentially take the grams of the element. So we would take the grams of the element, let's say carbon or hydrogen or oxygen individually, and essentially divide them. So we would divide them by the atomic mass of carbon. So if we were to say, okay, this is carbon, right? We're doing this formula for carbon. We would take the grams of the element and divide by the atomic mass of carbon. And so if you were to do this here, the first note and the first assumption is to assume that you have 100 grams of the compound. So you'll notice that each percentage, if you were to add them up together, the compound as a whole gets essentially adds to 100%. So if you were to say that, okay, this is 100 grams, that would be completely fine. And the reason behind that is because it doesn't matter how many grams of the substance you have. For this molecule, whatever this molecule is and however many atoms it consists of, you will always have, well, for this particular molecule, whatever the molecular formula is, you will always have the same amount of carbon, hydrogen, and oxygen in terms of its percent. And that's sort of the law of definite proportions. But if we assume 100 grams here, this becomes convenient because we can then say that carbon is 52.14 grams out of 100 grams. right? And you could do the same thing with hydrogen. You could say that this is 13.13%, or 13.13 grams out of 100 grams, or do the same thing for oxygen, where you could say that this is 34.73 grams out of 100 grams. So this gives sort of a valid unit onto carbon, which essentially helps us plug into this formula. So, if we assume that there was 100 grams in the compound, then we could just take, in order to sort of abide by this formula here, you could take 52.14 grams of carbon and then divide by the atomic mass. And of course, the atomic mass of carbon, if you were to look it up on a periodic table, is 12.01. And so if you were to do this, sort of this division here, you would in fact get 4.34. And in this, this unit would actually be in terms of moles. So you did that for carbon, and of course we have no idea why, but I'll tell you why in a bit. You did that for carbon, and of course you did that for, if you were to do that for hydrogen, I mean hydrogen has, so we did that for carbon. If we do the same thing for hydrogen, hydrogen has 13.13 grams out of 100 grams, if we're assuming the scale is 100. And if you divide that by the atomic mass of hydrogen, which is 1.008, you would essentially get 13.026 moles. And then if you did the same thing for your last element, which in this case is oxygen, well, oxygen, if you were to do this for oxygen, you would actually take the contribution in terms of grams, just 34.73. We'd have 34.73 grams over 16, 16 as the atomic mass unit for, or the atomic mass of oxygen. And then if you were to do this division here, you would essentially get 2.71 moles. So that was the first step, sort of plug into this formula here. And then of course, after you've done each for each element, you essentially want to take these numbers, right? So for carbon, you had 4.34, hydrogen, you have 13.026, and oxygen, you want to divide by the smallest amount of moles. So the smallest amount of moles here is 2.71. So you divide each by 2.71 moles. And essentially what you would get as sort of a consequence in this case is the answer you'd get here is 2, the answer you'd get here is 6, the answer you'd get here would just be 1. So you have 2 carbon atoms, and you have 6 hydrogen atoms and only 1 oxygen atom, and that is your empirical formula. That is your empirical formula. So this was clearly a very odd method, and it's a method that didn't make too much sense. But the explanation behind this method is very detailed, and it actually goes into why we're doing what we're doing. If I were to tell you to sort of forget everything that we've learned thus far in terms of the method, I'm going to show you why this is the case. So the first thing, I think we've already explained that we can assume that the compound is out of 100 grams or is of 100 grams, and then we can assume that carbon's contribution in terms of basically the idea is that you're assuming that there's 100 grams in the compound. So if you were to do 52.14% of 100, this would just give you 52.14 of 100 grams, that is. This would give you 52.14 grams. So, and it makes sense, of course, anything out of 100, if I had 30 marbles out of 100% of marbles, I just have 30 marbles out of 100. So, so carbon in this case is 52.14 grams, and hydrogen in this case is 13.13 grams, and oxygen in this case is 34.73 grams out of 100, right? And that's sort of our total out of 100 grams. The idea is, the idea here is to be able to find out how many atoms are in 52.14 grams of carbon, how many atoms are in 13.13 grams of hydrogen, and how many atoms are in 34.73 grams of oxygen. Once we have the amount of atoms, we can sort of write the empirical formula. Let's say I had X amount of atoms, right? Or actually, let me give some numerical quantity here. Let's say I had let's say I had some 2.34 times 10 to the power something atoms. And then for hydrogen, I had, some other big number. And then for oxygen, I had some other big number. Of course, it would be a very large number, but of course, I could express these large numbers here as moles. How many moles? So instead of having this big number here, I could say, well, let's say I had 4.34 moles here, right? Just to reduce the amount of atoms that I'm writing, or to reduce basically the tedious expression of atoms as being times 10 to the power something. But for hydrogen, I could have, let's say, 2.34 moles. And for oxygen, I'd have 7.8 something moles, right? And these, of course, just arbitrary numbers. But what I'm really trying to say is that if you could find out how many atoms are in each of these compounds in terms of moles, right? What you could do then is just divide. You could divide, this is basically just a ratio, right? 4.34 for carbon atoms in terms of moles, and then 2.34 moles of hydrogen in terms of atoms, of course, and then oxygen is let's say 7.8 moles, right? So what you could then do is sort of, you're left back to what we were talking about before, where you could divide each of these numbers by any number you want, and it would still be of the same proportion. It wouldn't be a changed ratio. It would be a changed ratio numerically, but it essentially wouldn't be a changed ratio in terms of, its value, right? Its bare value would be the same. And so if I can divide each of these numbers by any number that I want, why not it be a number which can give me a whole number, right? And so if you take the smallest number and divide each of them by this, so I have 2.34 moles here. If I were to divide each by 2.34, then I would obviously get a whole number back. And I would get a whole number back because if I take a big number and divide it by a small number, then of course the result will be a whole number. It won't be a fraction. And if I were to divide by a small number here in each of these cases, if I were to divide everything by 4.34, I'd get 1 here, that's fine. But if I were to do this, 4.34 moles, if I were to divide this out, I would essentially get a fraction, right? So I don't want to do that. I want a whole number. And so in order to get a whole number, I'll divide by the smallest, which is why you see them dividing by the smallest number here. So, so once you've done that, you essentially have, okay, let's say 2 moles, right? Or H is, 3 moles, and then oxygen is these many moles. And that's essentially what you would write for your empirical formula. Once you get that whole number, you can write those as your empirical formula. So you can see that it becomes pretty important to be able to get the amount of moles of atoms in each of these elements, or in other words, the amount of atoms. So insofar as doing so, what you would do in this case is you would essentially try to find out how many atoms are in 52.14 grams of carbon. And this brings you to Avogadro's number, which is to say that, well, you know that if you take the atomic mass of any element and express it as grams, then that amount of grams will have 1 mole, or 6.02 times 10 to the power 23 atoms for that particular element. So we know that the atomic number of carbon is 12.01. So if I were to take 12.01 grams then of carbon, then these many grams would have 6.02 times 10 to the power 23 atoms. In other words, 12.01 grams of carbon would actually end up having, it would end up having 1 mole atoms. Okay. And then if you want to figure, and so this is your conversion factor. And so if you want to figure out how many are in 52.14 grams of carbon, well, you would use your conversion factor to be able to figure that out. You would put 1 mole here so that your moles will be your final answer. And then you would put grams down here so that your grams would cancel out. And then once you do this division, which is actually just doing 52.14 over 12.01, you would get your number in moles. You would get 4.34 moles of, right? Because that's the only unit that's left over. You get 4.34 moles of atoms. So what this process, what this formula here is trying to have you do, it's still getting you to do 52.14 grams over 12.01, but it's not, it's sort of saving you from having to revisit this conversion factor or having to go through the process of going through this conversion factor and then doing that for every single element. That's very time consuming. So instead it says, okay, we'll just take your grams of element and then divide by the atomic mass, and then you'll get how many atoms. Well, the real story is that you're getting moles of atoms and you're actually dividing by the molar mass, right? And so this is why, you can just do this, and that's why it essentially works. So if you were to do this for each and every element, what you would do is you would get a particular amount of moles, right? For carbon, we know we would get 4.34 moles. For hydrogen, so you have carbon here, you have 4.34 moles. And for hydrogen, you would get, let's say, 2.81 moles. And for oxygen, you would get 3.64 moles. And these are, of course, random. But the goal is that these are atoms. This is a ratio of atoms. And so you would just divide by the smallest number, which is why they have you divide by the smallest number here, to get a whole number that is still equivalent to, that still expresses, in a sense, the amount of atoms that you have. So once you divide by the smallest number, which is 2.81, in order to get a whole number, not a fraction, you would have, let's say, you would have 2 moles, right? 2 moles, and you would have hydrogen as being you would have 1 mole in this case, because you would in this example you would have 1 mole for 2.8 moles, and then you would do this as well, and then let's say you get 3 moles or something. This would be your empirical formula. So your empirical formula is actually expressed in terms of moles, but it is a ratio. It is a simplified ratio. So that is the idea here. It's just saving you the trouble of having to go through that whole process, and then it's getting you essentially to the same answer. But if you wanted to be more sort of explicit about it, you could say that, okay, well, I have 52.14 grams of carbon. Okay, I have 52.14 grams of carbon. And now what you want to do is you want to find out how many atoms, or you want to figure out basically, you basically want to figure out how many atoms of the molecule in terms of moles, right? So what you would do is you could just say, okay, let me convert this to moles first. So in the back of your head, right? This is sort of in the back of your head, that the atomic mass of carbon, which is 12.01 in grams, equals to 1 mole. You want to figure out how much is 52.14 grams. You just do 52.14 multiplied by, and you would take this ratio in such a way that your grams would cancel out. You would have 12.01 grams and then 1 mole. and your grams would cancel out just like that. And you would be left with doing this division problem, 52.14 over 12.01. And your answer would be in moles, and that would be carbon, let's say 4.32 or something like that. And that would be your ratio in mole. And you were to essentially follow the same process for each and every single element. And then once they are expressed in terms of their ratios, so once they're expressed in terms of carbon, hydrogen has a certain amount of moles, and then oxygen has a certain amount of moles. Once this ratio is expressed, you divide by the smallest number to get a whole number. And that's essentially what's going on here. And so that's essentially the way to do it. And so once you have that quantity, right? Once you have that quantity, let's say we said that we have C for this particular answer. I think we said we had C2. The answer was C2H6. So you have C2H6O1. And that's essentially your, that would essentially be your empirical formula. For part B, it says, okay, the molar mass of the compound is this much. What is the molecular formula? This brings us to acknowledging the fact that the molecular formula is but a multiple of the empirical formula. In other words, if to just sort of draw a metaphor here, if I said that, the empirical formula in this analogy, the empirical formula is, let's say, 1/4, okay, and the molecular formula is 1/12. 1/12. The molecular is twice that of the empirical, right? Because if I were to multiply this by 2, my bad. I would have to have 16 down here. So if I were to multiply this by 2, then I would get my molecular. So the molecular in this case, whatever it is, we don't know what it is yet in this case, it's going to be a multiple of the empirical, because the empirical is a reduced version of the molecular formula. So the molecular formula is it's a multiple of the empirical formula. And in order to find out the molecular formula, we want to figure out what is the basically, this is the way you would figure out the molecular formula, leveraging this fact. What you would do is the molar mass of the molecular formula. That is something that you just know because the question provides it. The molar mass is 138.204 grams per mole. That's the molar mass. Now, if you were to find out the molar mass of the empirical formula, right, and this is of course the molecular formula. If you were to find out the molar mass of the empirical formula, and that comes out to, let's say, I don't know, any number, you know that the molar mass will be some factor greater than the molar mass of the molecular formula will be some factor greater than the molar mass of the empirical formula, right? And so what you would do is you would find the molar mass of the empirical. Let's say that comes out to being, I don't know, 46.068. Then you know that 138.204, which is the molar mass of the molecular formula, is sometimes greater than the molar mass of the empirical formula. So what you do is you would take the molar mass of the molecular formula, which is 138.204, and divide by the molar mass of the molecular formula, which is 46.068. And then once you do this, you'll essentially get a whole number. And once you get that whole number, this essentially tells you how many times greater is the molecular formula than the empirical formula in terms of its grams per mole. just as if you had, just as if you had 1 over 4, or let's say you had 4 and you had 12, you know that the molecular formula, or 12 in this case, is sometimes greater than 4. How would you figure that out? You would do 12 divided by 4, right? This would give you, well, okay, you want to use 16 in this case, but if you had 16 over 4, you'd know that 16 is 4 times greater than 4. And so 16 is greater than 4 by a factor of 4. So, and so really my point is, once you figure out how much the molecular formula is greater in terms of its factor, you would multiply each subscript of the empirical by that factor. So the molecular formula would be 6 times 3 times 2. So it would be 3 times 2, which is just 6. And then, and then you would just, let's see here, we have 6. So 6 times 3 would be 18. And then O for oxygen, we know that we only had 1 mole of oxygen in this case. So you would just do 3 times 1, which would just be 3. And that would be your molecular formula.